and just click
Okay.
recording.
Okay, welcome everyone. So what we're trying to do here with this mini course is really improve the amount of sort of interactiveness and engagement that participants have in these kinds of online settings by and those problem sessions are kind of the main vehicle. So let me reiterate what Gluchuan said and sort of recommend that you take a look at those and maybe form groups and work with them, and then we'll meet starting next week to discuss the solutions. Okay, so what we're gonna my plan here is to talk about stable homotopy groups. Okay, and what I really want to focus on is how to actually compute with the atom spectral sequence and related matters. Okay, so and consequently, this is aimed at an audience that doesn't necessarily have a lot of background in the atom spectral sequence. Okay, so we are not going to be talking about recent progress. That's not the purpose of these 3 lectures, is to talk about the latest and greatest techniques. And it's not about stable homotopy groups in the high dimensions and the highest dimensions that we currently know how to compute. It's none of that kind of current up-to-date research results. It's also, it's not a description of the latest techniques, the latest, most modern techniques, such as the use of motivic homotopy theory and the use of deformations of stable homotopy theory in order to study homotopy groups. Okay, this is all very interesting stuff. This is the stuff that I work on, that I'm currently working on, that I'm making progress on, but that's not the subject of this this series. Another thing that this series is not is I am not going to carefully construct the atom spectral sequence from first principles. And I'm not going to talk about convergence issues for the atom spectral sequence. If you are interested in this material, I highly recommend at some point you go and look at how the atom spectral sequence is actually constructed. And my recommendation as a source for that, I highly recommended John Rognus's lecture notes. Okay, these are unpublished, but they're available on the web, and there's a few different versions of them, and they all do an excellent job of covering these basic fundamental foundational issues regarding the atom spectral sequence. Okay, so there's a bunch of things that we're not going to do, right? So what are we going to do? Okay, well, we're going to talk about the sort of practical skills that are involved when you're trying to manage a complicated spectral sequence. If you've got some spectral sequence of your own that you would like to compute, then many of these skills that we're going to be talking about over the 3 lectures could potentially be of use for you in organizing your information and keeping track of the details. We're going to talk a lot about algebraic tools, tricks, methods, techniques for how to handle all this information, sort it, and keep track of it. We're going to work through lots of examples to illustrate all of these points. Okay, and just as a blanket statement, this isn't really a goal, but it just sort of fits in here in the introduction. I'm always going to be working to primary. Everything that I'm working is at the prime 2. Odd primes are interesting. There's lots of stuff to do there, but that's not at all what we're going to talk about. For expository purposes, say we're always going to be working at the prime 2. Okay, so before we actually get into all of these practical skills and so forth, let me give you a slightly kind of bigger overview of sort of how I see this sort of computational aspect of stable homotopy theory. Okay, so my view of this is what I call a sort of a Mahowaldian philosophy. Okay, and it's indicated in this diagram that I've drawn here. There are 3 components to this philosophy. There's theory, there's manual computation, and there's machine computation. Okay, and each of these 3 parts kind of feeds on and interacts with the other parts. So, for example, you develop theory that leads to new techniques for computation. Okay. On the other hand, when you carry out a manual computation, you start to see patterns and notice structure, and that provides hints to new theory. Okay, so that's these arrows here. This relationship between theory and manual computation. And similarly, manual computation and machine computation play off against each other. Manual computation could be viewed as like a preliminary test for a more extensive machine computation, or on the other hand, machine computation verifies and extends the results that can be only carried so far by hand. Okay, I see all three of these components as essential ingredients in this program for, say, computing stable homotopy groups, or carrying out other computations in stable homotopy theory. Okay, and one of the ideas that I really like to emphasize, because I think that that it goes against a lot of people's intuition, and it may not have necessarily occurred to everyone, that in my perspective, computation precedes theory. Okay, we're sort of used to seeing, say like in textbooks where the author discusses the theory first and lays it all out very beautifully, and then at the end maybe there's a chapter on applications or something like that, and do some computations. And from an expository perspective, I can understand why you would have theory preceding computation. But down in the trenches, out in the real world, that's not how progress is made, right? We carry out the computations. We do speculative computations. We compute things that we're not even sure exist and see what happens, okay? And then that leads to new ideas. Theory. This, of course, is not the only way to do mathematics, but it's the perspective that I have taken, and it has gotten us some places. Okay, so I want to illustrate this idea of computation preceding theory with two historical examples. Okay, so one example was that many decades ago, Mahowald observed that you could take the cohomology of A of 2. Okay, so this is some algebraic object. If you don't know what all these symbols mean, don't worry too much about it. But he noticed that there was this homological algebra thing, okay, and the cohomology of A of 2. And he saw, just by studying its structure, he saw that it was plausible that this was an Adams E2 page. It looked like maybe there would be a spectrum whose E2 page, Adams E2 page, was this thing. Okay, and then and this observation preceded the construction of the spectrum TMF, which is the spectrum whose atom spectral sequence is E2 page is given by that. Okay, so Mahowald's observation was really the beginning of the search for TMF. Okay, which is a sort of a major piece of late 20th century stable homotopy theory. Okay, so and I would love, I love this story, and I sort of, I keep this in mind all the time, and I'm sort of trying to relive this, right? I'm trying to kind of see what is the next thing out on the horizon by studying the computations and looking for the patterns, okay? And another more recent and more personal example is that we spent a lot of time computing C-motivic stable homotopy groups just by brute force, just by doing it, before we finally realized we had this conceptual breakthrough that C-motivic stable homotopy theory is a deformation of classical stable homotopy theory. Okay, and this deformation is the sort of a very modern, very up-to-date perspective on all of these things. But again, these realizations came out of extensive computations. Okay, that was the computations preceded the theory. Okay, so this is just kind of sort of some general background, some philosophy on the way I see how these computations fit into maybe the bigger subject of stable homotopy theory. Okay, and that's the introduction. Okay, so that's sort of a separate component of all of these talks. Okay, and now what I want to do is shift right into the concrete details. Okay, so what I want to talk about today is filtered objects and their associated graded objects. Okay, so the point is that a spectral sequence, what does a spectral sequence do? It doesn't actually compute the thing that you want. What a spectral sequence does is it computes an associated graded object of a filtration on the thing that you want. Okay, so typically there's this thing that you want, but you don't actually get it. You get this sort of associated graded, and you think, well, this is sort of a shortcoming. It's like a loss of information. You end up with all these relative quotients between these filtration layers, but not actually the thing itself. Okay, and that is a perspective, and depending on what you're doing, that could be a problem. But the way I look at this is that the filtration itself is rich additional structure on the thing that you're trying to compute. If you're computing something with a spectral sequence, then it turns out that that target isn't just an abelian group or a module or something. It actually comes with a pretty natural filtration, and you should be studying that filtration as well as studying simply the abelian group structure. And that's what the sort of the spectral sequence approach really forces you to take this filtration seriously. Hey, but it turns out that this filtration, it's useful additional structure. It's not just there, and it doesn't just complicate your life. It actually helps you along the way to your complication. It aids in the analysis of that target. Okay, so as a result of this, what I prefer to do, I prefer to work with Adams E-infinity pages. If I want to look up some information about a stable homotopy group, I don't want to look at a table of abelian groups, Z mod 8 plus Z mod 16 plus Z mod 32 plus Z mod 2, something like. I don't want to see that. What I want to see is the Adams E-infinity page. And when I look at the Adams E-infinity page, and that's what I'm getting here is the associated graded object of the stable homotopy group. I prefer that picture. That gives me more information because it keeps track of this filtration. And then if I ever need to resolve these extensions, and we'll talk about what that means in a little bit, then I just do those on the fly. Okay? If I'm working on a particular problem and I need to know some extension, I'll work that out, maybe record it, write it down someplace, but then go return to the Adams E-infinity page when I'm done with that specific point. Okay. So what I'm talking about here really is how to read an Adams E-infinity page, and we will at some point later we'll actually look at some charts and we'll see kind of how all of this works. Okay. All right. So I just mentioned this rich additional structure in the filtration, and I want to point out that this rich additional structure, this is a recurring theme. It will come out at least once more in the second lecture. Okay, and the point is that you can't get away from this additional structure. You really want to pursue it. You seek it. This is where all of the valuable stuff lies. And so one way of sort of kind of.
Excuse me. Yeah, it seems the slides are frozen.
Is it? Yep, it is. Okay. Excuse me 1 second. Let me fix the problem. Sorry about that. This is going to take me just a minute or two to get it sorted out. I had a feeling that there would be a minor problem here, but I think this is going to fix it. Okay. Okay, you should be able to see my screen again. Is that right?
Yeah.
Okay, and does the sound still good?
Yes.
Okay, terrific. All right, so let's keep going. Okay, so I was talking about rich additional structure, and so the point is that if you consider the stable homotopy groups and you take all of its additional structure, and I put all in quotes because there's an important point here, is that we don't even know how to describe or name what all of the additional structures. We know what some of the additional structure is, or what we're looking for. We don't even know what we're looking for when I say all additional structure. But if you take all of the additional structure, then what you have encoded is the entire homotopy category of spectra, or maybe you need finite or finite type down at below or something. But you basically encoded all spectra into just the stable homotopy groups with all structure. Okay, so there's maybe 2 points here. One is that you can't ever actually expect to get your hands on all of the additional structure. And on the other hand, but you definitely want to get your hands on whatever you can, because it's telling you a lot about spectra more generally than just the sphere spectrum, maps from the sphere spectrum to itself. Okay, all right, let's talk a little bit about notation. You know, notation itself is an important part of organizing and carrying out a complicated spectral sequence. My perspective is to choose whatever notation works best for the problem at hand. Okay, a notation is good if it is helping you keep track of the details, and it is bad if it is interfering with the details. And one of the things that that means is that you should not be afraid to change the notation from what's been used by previous authors. Just because a previous author used a particular letter and a particular subscript for something, it doesn't mean that you have to stick with that particular choice forever. It may have been that from one perspective, a certain notation is useful, and from a different perspective, a different notation is useful. So don't be afraid to change if that's what, again, it's whatever works. It's a very pragmatic approach here. It's whatever works is what's best, okay? So when I index a spectral sequence, when I choose how to index a spectral sequence, what I do is I start with a convenient notation for the target. Okay, and then I work backwards to whatever notation that implies about the previous pages of the spectral sequence. Okay, so let me give you an example here. So here is a way that the atom spectral sequence is often indicated. Okay, so you have X over the Steenrod algebra, S comma T, there are these things bigraded, there's 2 degrees, S comma T. S is the homological degree, right? X is derived functors of Hom, and so that S is the homological degree associated with that derived functor, and then T is the internal Steenrod algebra degree. This A is a graded algebra. It has an internal degree, and that's what the T represents. Okay, so S and T are natural choices for the E2 page of the atom spectral sequence. But the problem is that it then converges to pi T minus S. And that's not such a convenient notation for the target. What I'm saying is down here, turn it around. Start with a good notation for indexing for your target, pi n, and then work back and figure out how to index this E2 page. Even if it's not natural from the perspective of homological algebra, it will be more useful to you because it aligns with the notation of the target. And so that's what I've done here. And this is the way that I index X groups for this very reason. I use this, two numbers, N and S, where S is the same homological degree as before. That one I leave the same, and that's the same as the Y coordinate on an atom's chart. Okay, but then I use T minus S instead of T. I use T minus S as the second grading, and that's the atom's chart X coordinate, and that aligns up with this dimension of this stable homotopy group, and that ends up being a lot more useful. See, look, for example, right? Let's say I'm interested in what's going on in the atoms chart at degree 17,4. Well, I would write X 17,4, and I immediately know where to look on a graphical chart. 17 over 4 up, 17,4. Okay, 17,4 in this notation, 17,4 would be written 4,21. Okay, so then I have to take 4,21 and I have to subtract them to get the X coordinate 17, and then I have to switch the order and put the 4 at the end for the Y coordinate, and that's not that big of a deal, except if you're doing it 100 times a day or 1,000 times a week, then that little bit of sort of like inconvenient notation ends up slowing you down, and it's just in the way. And why do you have to do that? Don't do that, right? Don't torture yourself. Okay, and the other thing that I would recommend, in addition to sort of focusing on the target and working backwards, is that what I always do is I re-index these spectral sequences so that the associated graded objects are aligned in vertical columns. Okay, so, and that's the way that the atom spectral sequence is graded. So as an example, let's talk about what this means about the Serre spectral sequence. Okay, so the Serre spectral sequence S is associated to a fiber sequence F, E to B. Okay, and we can make things simply connected, and we can add in all the extra hypotheses we need, just in the simplest case. So the same thing applies in general, but I wrote down the simplest case where the E2 page is the cohomology of the base, tensor the cohomology of the fiber, and that converges to the cohomology of E. Okay, and this is sort of the way that you would usually see the Sayre spectral sequence written, and this is the way that you usually see the Sayre spectral sequence graph. You have the cohomology of B along the x-axis, you have the cohomology of F along the y-axis, and then the associated gradients of the cohomology of E lie along these diagonal lines. These are the lines where P plus Q is constant. Okay, and so then if you're going to reconstruct the cohomology of E from a spectral sequence, you have to look along these diagonal lines. And to me, that's kind of annoying and distracting. It's just hard to keep track of things that way. Okay, so what I would recommend, the way I think about the Sayre spectral sequence, I don't actually use the Sayre spectral sequence that much, but if I were going to use it a bunch, I would re-index it this way. Okay, and then the result would be that the cohomology of B would be along the x-axis. The cohomology of F would be along a diagonal line, pointing up and to the right. Okay, and then the dr differentials would go over 1 and up r, and the associated gradients for the cohomology of E that would lie in a vertical line. So if you're studying H15 of E, it would all be along this line where x equals 15 and so forth. Okay, now I know that, so what I'm talking about here with this Sayre spectral sequence is the idea that you know the cohomology of B, you know the cohomology of F, and you're studying the cohomology of E. I know the Sayre spectral sequence is sometimes used in more complicated ways where you know the cohomology of E and you can deduce the cohomology of B and the cohomology of F from that and so forth. So maybe in those situations, you might want to do something a little bit different. But in this case where you're proceeding from left to right, I prefer to organize things this way. Okay, again, you don't have to do it this way. I'm not telling you you have to do it this way. I'm telling you, sort of, I'm sharing with you my experience, what's worked for me in the past, and these, you know, these tips may or may not work for you as well. Okay, but this is a good example of not being afraid to change the notation. You look in the textbook, this is how it's drawn. Don't be afraid to redraw the spectral sequence if that ends up being more useful for you. Okay. So let's get into some of these details about filtrations and things. All right, so I'm thinking about A and B being abelian groups. Okay, you can certainly do this more categorically. A and B could be R modules, or A and B could be things in an abelian category or something like that. But A and B are just abelian groups. Okay, and everything inside here is finite. All these, you know, everything is, all the filtrations are bounded below, all the filtrations are bounded below, they're complete, they're housed, I mean, they're all well behaved. Okay, I'm not going to get into all the sort of the pathologies that can occur with, you know, these convergence issues, because I'm just going to assume them away. Things are well behaved. Okay, so we've got two abelian groups, A and B, and they have decreasing filtrations, F star A and F star B. Okay, they're filtered objects, they're sequences of subgroups, decreasing sequence of subgroups. Okay, and then they have associated graded objects, GR star A and GR star B. So GR P of A, you take the Pth stage of the filtration and you mod out by the slightly smaller P plus first stage of the filtration. You get a quotient, and that's the graded. That's the graded part of the GRP of A. Okay, and you take all of these, you add, and you take their direct sum, all the different P's, and that's GR star of A. Okay, and remember that that in the context of a spectral sequence in particular, the atom spectral sequence, just to remind you, A is like a stable homotopy group, and G star A is like the E infinity page. Okay, that's what we actually get from an E infinity page. We're actually told what G star A is, not A itself. Okay, all right. So so what we have to do is learn how to work with these graded objects and learn how to deduce information about A from the graded objects. And that's roughly speaking what we're talking about here. Okay, all right, so take an element in A. Okay, I guess it better be non-zero. Okay, then what happens is that X is in some stage of the filtration, okay, but not in the previous stage. Okay, so you have this decreasing sequence of subgroups, and you find the last one that contains X. Eventually, the subgroups go to 0, and so there's a last one that contains X. Okay, that's why I need X to not be 0. So there's a last one that contains X. Okay, so FP is the last. Do I have this the wrong way around? Yeah, I think I want this to be F plus 1. Okay, great. All right, so then what happens? So this is the last one that contains X, and then what you can study is you can study X bar in this quotient, right? Because X is an FPA, then there's an X bar in GRP of A. Okay, so notice though that this is kind of a funny, this is sort of a, not exactly well, it's a function, but it's sort of a funny behaved function in terms of sources and targets, because you start with something in A, but where it lands depends on sort of its properties with respect to the filtration. Okay, so but anyway, so it's not a function from A into the associated graded. It just sort of like works element by element. Okay, so that's notation that we're going to use, and that's really kind of the way we want to think about. Here are these elements X. These are like stable homotopy elements, and what we really have is we know about their E infinity images. We know about their X bar, about its image in E infinity. Okay, and we want to study X using X bar. Okay, now one of the things that comes up when you're studying Adams E infinity pages is there are filtration preserving maps all over the place. Okay, and we'll talk about where those come from in a minute. But for now, let's just suppose that you have a abelian group homomorphism from A to B. Okay, and I wrote B bracket K because what I want this F to be a filtration preserving map, not just any old homomorphism, but it should preserve the filtration. Okay, and but the way things work in practice is that I want to be able to shift the filtration index, and that's what the K represents. And so a filtration preserving map would take F of FPA would have to be an FP of B, but if I shift B, then F of FP of A is contained in FP plus K of B. Okay, that's the sort of thing I want to be able to do because that's what arises in practice. Okay, well, such a map induces a map on associated gradeds. You just check that the denominators of these quotients go to the denominators, and it all works out just fine. Okay, so you get an induced map on associated gradeds. All right, now what happens again in practice is that we're seeing in the Adams E infinity page, we're seeing GRF, and maybe we want to reconstruct information about F itself. Okay, so if we have F, we can get GRF, but it's really the other direction that's the more interesting and the more practical one, the one that actually occurs. All right, so typically, and I say generically, and I'm not using that in any precise sense, I just mean sort of typically the easy case, the base case is that if you start with, if you take a non-zero value of this map F, say F of X is not equal to 0 in B, okay, then typically GRF of X bar is non-zero in GRB. Okay, so in other words, typically, if you have a non-zero map value of F, it's seen as a non-zero value of GRF. Okay, but that's not what happens all of the time. Some of the time, it's possible that the filtration of F of X is actually strictly greater than the filtration of X. It could be, since F is filtration preserving, that puts a lower bound on the filtration of F of X, but it might be that the filtration is actually even higher. Could be just sort of coincidentally, okay, in a special case. And this does occur frequently in practice. Okay, then what happens is that the associated graded map applied to X bar is actually 0, even though that original F of X was non-zero. Okay, what's happening here is that when you take the associated graded and you take all of these quotients, you're losing some information, and there's a non-zero value of F that's not being detected by the map on associated gradeds. Okay, and so we call that I call that a hidden value of F. Okay, and you may often hear the expression hidden extension in the discussion of stable homotopy groups, and that's the same thing. It's essentially a hidden value of a particular map when we talk about hidden extensions, which is exactly where we're going. Okay. All right, so let's get a little bit more concrete. Okay, there is an element eta in pi 1 in the stable homotopy group, in the first stable homotopy group. Okay, the first Hopf map. Okay, so multiplication by eta induces a map from pi n to pi n plus 1. Okay, so you have a map from pi n to pi n plus 1, right? But that map then is seen when you look at Adams E infinity pages. These are associated gradeds for these two groups. E infinity is associated graded for the source. E infinity bracket 1 is associated graded for this other guy. Okay, and that's that bracket 1. That's that shift again, because that's the way that eta ends up shifting the filtration. Okay, so you have this map on associated gradeds, and the atom, and so when you look at the E infinity page, you know this map, you read this math right off of the dots and lines, and we'll talk about that later. Okay, and when you want, maybe you want to learn something about how eta actually works. Okay, and when you hear about a hidden extension by eta in the stable homotopy groups, it's precisely a hidden value of this map. There's a non-zero value here, but it's not seen at this level. At this level, it takes it just goes to zero. Okay, so let's draw some pictures. Okay, and look at an example here. Okay, so what I've got here is a little snippet of the sort of thing that you might see on an Adams E-infinity page. Okay, so this is like, this vertical column is like an associated graded for pi n, and this vertical column is like an associated graded for pi n plus 1. Okay, so this has 3 stages to the filtration, and this has got 2 stages to the filtration, and they've got these different, the different degrees. And then the filtration is sort of plotted on the vertical axis. Okay, so you're going up is higher filtration as you go up the picture. Okay, so what does it even mean to have these sort of 3 dots here? Each of these dots is supposed to indicate a copy of F2 or Z mod 2. Okay, so up here, the top piece of the filtration, well, that's actually a subgroup of the stable homotopy group, because there's no higher quotient, there's no higher piece, there's no quotient there, you're just mod out by 0. So here there's a Z mod 2 inside of the stable homotopy group, and let's call alpha 1, let's just give the name for that unique non-zero element there. Okay, so I'm going to label that with an alpha 1, meaning alpha 1 is the unique non-zero element there. Okay, detected by that at that filtration. Now, what about this dot? This is another F2, but really this dot is actually detecting 2. See, now there really is a quotient here. You're saying that that F2 modulo F3 is Z mod 2, but F3 is Z mod 2. And so this F2, the second stage of the filtration, is actually a group of order 4. Okay, so let's let alpha 2 be, and okay, so I guess there are 2 elements here. There's 0 and there's the non-zero element. Okay, the 0 element here corresponds to 2 elements of the stable homotopy group. It corresponds to 0 and to alpha 1. Those are the 2 elements of F3. But then there's a non-zero element here, and it corresponds to, let's say, alpha 2, and we'll just choose alpha 2 to be one of the non-zero elements here. Okay, but then this same dot also, so there's an epsilon 1 here, and I mean by these epsilon coefficients, I mean it could be 0 or 1. Okay, so there's really 2 elements that are detected by this non-zero element. There's alpha 2 and there's alpha 2 plus alpha 1. Okay, similarly, this dot, this non-zero element is actually detecting 4 elements. So choose 1 to be alpha 3, and then you could add an alpha 2 if you want to that, and you could add an alpha 1 to that, and you get 4 non-zero elements that are all detected by that same dot in the associated graded object. Okay, remember, these are associated graded elements, and then what's in red is back in A itself, back in the actual stable homotopy group. Okay, same thing over here. There's a beta 0 at the top, and then there's a beta 1 plus some coefficient, possibly a coefficient beta 0. So there's 2 elements here that are detected by that non-zero element. Okay, now, so far I've only talked about the dots. Okay, and now then there are these lines. Okay, so these lines are a graphical representation of this map, or rather this map on E-infinity pages. Okay, and so a line is connecting a source to a target. Okay, it's saying that GR eta of this element equals that element. Okay, and that's expressed when you lift that back to pi n and pi n plus 1. What that's saying is that eta times this alpha 1 equals this element beta 0. Okay, so there's this relation here in the stable homotopy groups that's expressed by that line. Okay, but now there's this dot, and this dot you see has no line coming off. Okay, so what does that mean? What that means is that eta times one of these elements is 0 for some, so for some value of epsilon 1. Okay, so it could be alpha 2, or it could be alpha 2 plus alpha 1. One of these elements, when you multiply by eta, you get 0. But then notice what happens when you take the other one, and that's what 1 plus epsilon 1 does, right? It switches between 1 and 0, right? It switches the coefficient. 0 becomes 1, 1 becomes 0. So if this guy is 0, then eta times this guy, what have I done? I've added alpha 1. Add alpha 1, and then I'll get beta 0. Okay, so there are 2 elements detected by this guy, and in this particular situation, one of them is killed by eta, and the other is not killed by eta. It's actually that beta 0 up there. Okay, so one thing that you do in practice in this situation like this is that you'll use this relation eta alpha 2 equals 0 to define alpha 2. Remember, alpha 2, there are sort of 2 elements that you could choose here for alpha 2. But only one of those 2 elements actually is killed by eta, and that could be a definition of alpha 2. And that's something that we often do in practice. Then you have to keep track of those definitions. And I'll make a remark here. You have to be careful when you define away these hidden extensions like this, like I'm doing right here with alpha 2, because you're making some choices for 2, some choices for eta, some choices for new, some choices for other extensions, and you have to make sure that your choices are compatible. If you make one, and it's not always the case that the most convenient choices for these different maps are always the same. Sometimes a choice for one is convenient, and then it makes the other one complicated, and you have to learn to live with that. Okay, all right, we're almost done with this one. Let's look at this sort of last thing. What about these 4 elements down here? Okay, now what I've drawn here is a dashed line, and that's to indicate that there's actually a hidden extension. On E infinity, you apply the map on E infinity to this element of E infinity, and you're gonna get 0, okay? But what happens in the homotopy groups is actually there is a non-zero value here that's not seen by E infinity, okay? And what I'm saying here is that eta times one of the 4 elements here equals one of the 2 elements here. That's what this dashed line is saying, is that one of these elements equals one of these elements. Eta times one of these elements equals one of these elements, okay? Well, but then what you could do is you could change epsilon 1. You could switch epsilon 1, or in other words, add alpha 1 to this, and then you could kill off a beta 0 term. If you happen to have a beta 0 term here, you could add alpha 1 to this, and that would kill off the beta 0. So you can arrange for eta times some element to equal beta 1. Okay, but then notice what happens is that eta times the other element, another element, is then beta 1 plus beta 0. Okay, so amongst these 4 elements, what's happening is 2 of them are, you're getting, amongst these 4 elements, you're getting both, here there are 4 elements, here there are 2 elements. And if you take these 4 elements and you multiply them all by eta, you're gonna get both of these elements, okay? 2 will go to 1 and 2 will go to the other one. That's what I'm saying here, okay? So when you take these kinds of pictures and you break them down, you give names to the elements that these things are representing, and you break down what's actually happening on the stable homotopy group, you sort of learn how to go back and forth between these things. Now, again, all of this analysis over here on the right, this is what I would do sort of on the fly in some specific situation. If I wanted to get into details and untangle some sort of difficult, complicated thing, I would use this sort of notation. I would write things out like this. Normally, I just draw this picture and I don't even put in the alphas and the betas. I just see the dots and the lines, and I know that what that encodes. And if I have to make choices, then later, then I'll worry about it. And that's what I meant when I said earlier, I prefer to work with E infinity pages and just do things on the fly. Okay, let's see here. How are we doing on time? We're doing okay. All right, so we're going to look in, later we're going to actually look at some Adams charts, and we'll see pictures like this. And there's lots of variations on this sort of thing. And in the exercises, I have some other situations for you to analyze similarly. Okay, so you can apply these ideas and sort of sort out what is actually happening in some other E infinity situation. Okay, now I work with eta because the nice thing about eta is there's 2 different groups, and then the source and the target are different, and it's actually a little easier to think about. What happens with multiplication by 2 is actually a bit more complicated, because now you have a map from a homotopy group to itself. Okay, so again, you get a map on E infinity pages. Okay, and if you can figure out what happens to multiplication by 2 on pi n, then you can determine the group structure of pi n. Okay, E infinity does not tell you the group structure of pi n, but E infinity together with the effect of multiplication by 2, when you put it together, that will tell you the effect of multiplication. Okay, so again, you could be, some people might say, oh, just tell me what the group is. I just want to know what pi 63 is. Just look it up and you'll have the answer. But that's not how I prefer. I would rather see the map on E infinity pages and the hidden to extensions as extra information. To me, that sorts the information in a more convenient way with that rich additional structure that helps me keep track and understand what's going on. Okay, so 2 quick examples. And again, these are the kinds of pictures that you would see on an Adams chart. Okay, so in this one, this is an example of an abelian group with a 4-stage filtration, 1, 2, 3, 4. Okay, this associated graded is F2, F2. Here is F2 plus F2. Okay, it's an abelian group of order 4. It could be that more than one dot's in the same filtration. And then there's an F2. Okay, and then these vertical lines indicate the effect, the map on E infinity, multiplication by 2 on E infinity. It's saying that a representative of this, an element of the homotopy group represented by this dot, you multiply by 2, you'll get something represented by that dot. And from this sort of picture, it's really easy to end up reading off the abelian group structure. This length 3 chain is representing a Z mod 8, 2 cubed, and this length 2 chain is representing a Z mod 4, Z mod 2. Okay, so you kind of piece these Z mod 2s together to form groups of larger order, and the lines tell you exactly how to do it. Okay, and just as another illustration, there can be hidden extensions. So there could be a 3-stage filtration, and there could be a hidden extension from the lowest dot up to the top dot, and then those 2 dots together form a Z mod 4 in the homotopy group, and then this dot by itself forms an element. It gives you another element of order 2. You get Z mod 4 plus Z mod 2. Okay, again, I actually prefer these graphical, these pictures rather than these group elements because it's giving me more information. All right, so I keep promising you that we'll look at some Adams charts, and so let's actually go ahead and do that now. Okay, all right, so I'm going to pull up here. This is the one I want, and we'll zoom in a little bit. Okay, so this is an E infinity page. Okay, where this comes from is sort of not particularly relevant today. Today we're talking about how you read this chart. That's what we've been doing today. Is we've been talking about what all this notation that you're looking at on the screen, what it actually means. Okay, so what happens? Let's see, where do we want to start? Well, okay, let's start at the beginning. Here you have this infinite tower. And that's a kind of a special case because I said, let's just assume all the filtrations are finite. But here in the 0 stem, you actually have an infinite tower, and that's assembling into a copy of the 2 adic integers. You can filter the 2 adic integers, and all of the quotients are all Z mod 2s, but then in the inverse limit, you get Z2. Okay, so that's represented there. There's only one dot, that's easy, that's a Z mod 2, that's a Z mod 2. Here there are 3 dots connected by vertical lines, that's a Z mod 8. Okay, pi 3 has a Z mod 8. Okay, and pi 7 has a Z mod 16, and so forth. Okay, so we're reading these things off. Up to this point, so this is sort of many of you probably, some of you probably have looked at the Adams spectral sequence before, and you may know about this sort of first Adams differential. We're not seeing it here because this is the E infinity page, but H4 supports a differential, a D2 differential right there, and that's why it's gone in the E infinity page. But anyway, it's sort of well known that the first sort of topological phenomenon in the Adams spectral sequence occurs around 14. In other words, everything less than 12 is purely algebraic. You do an Ext homological algebra computation, and you get an exact computation of stable homotopy groups. Okay, that's what happens up to up to stem 13. But that actually is not true. Okay, there's actually a not so well-known fact about the stable homotopy groups that is not seen in the algebra up to this point. Okay, I want to look right here at this dot right there. Okay, what's happening there? When you look at the algebra, you have you have two lines coming together, and that's giving you a relation. It says that in algebra, h1 cubed plus, hang on a second, let me change this, plus, that's a little better. h1, oops, let me try again. h1 squared times h3 plus h2 cubed. Okay, it looks like that sum is 0. Okay, well, it is 0 in algebra, in X, in E infinity. That sum is certainly 0. And what that makes you think is that eta squared, eta is detected by h1. Eta is the homotopy element detected by the E infinity element h1. Eta squared times sigma, sigma is detected by h3, plus nu cubed, that's detected by h2. You would expect that to be 0. But actually, here's the surprising and unknown fact. Actually, eta squared sigma does not equal nu cubed. There's an error term in higher filtration. The error term is right there. And here, you know what? We can use a different color. The error term is right there. The difference between these two is actually a non-zero element called eta epsilon. Okay, I call this Toda's relation. It's in the work of Toda. I'm not 100% sure that that's where the first place that it comes up, but it probably is. Okay, and this actually is a piece of a little bit of the structure of pi 9 that is not seen in algebra. This is probably really is the first topological thing that's not seen in homological algebra. Okay, so you can, you know, this is a little bit of a more complicated situation than the extensions, the two extensions and the eta extensions that we were talking about earlier, but it's the same kind of thing, that there's sort of, you know, there's some relation that looks like it's 0 in E infinity, but it turns out actually it's not, it's in higher filtration. And it's the same kind of, you can set it up with a little more complication. I didn't have time to today, but you could set it up in a way and actually kind of fit it into that same framework. Okay. All right, so here's the E infinity page. Let's scroll a little bit to the right. There's just there's more data here. You see some long towers. There's a Z mod 32 there in pi 15 and so forth. And this red line here, this is actually the first hidden 2 extension. Okay, if you compute the infinity page, by and large, you've got the abelian group structure, except right here, this is the first hidden 2 extension. Okay, that's just the way it works out. And you can see these green and these blue lines. The blue lines are hidden eta extensions, and the green lines are hidden nu extensions. So others of these actually occur a little bit earlier. Okay, so you might be wondering, well, how do you figure this out? I mean, let's say you have the E infinity page. How do you decide whether or not there's a hidden extension there or not? Well, that's a good question, and we're going to talk about some of those techniques in the later lectures. For today, again, we're just looking at these charts and learning how to interpret them and how to read them, you know, and just get familiar and navigate. We're not talking so much about where they actually come from. Okay, what else do I want to say? I mean, you can go into higher stems and things start to get more complicated. There's another hidden 2 extension in the 40 stem, another 2 extension in the 47 stem. This one in the 51 stem is interesting. This one is hard, turns out. This one with this, you know, some of these are not so difficult. You can fiddle around and figure them out, deduce from other, you know, structure. This one's difficult, and it sort of came late in the game. That's just the way it unfolded. And this one is sort of interesting because we knew for a long time that there was a 2 extension on this element, but we didn't know the target. We knew that there would a 2 extension from here to here or from here to here, and we couldn't sort out which one was which. And that sort of had implications for more complicated relations in multiplicative relations. And it was finally sorted out by Robert Birkeland. Finally ended up deducing that it is in fact that longer extension that happens there. Okay, so as you go into higher stems, as you might expect, things start to get more difficult. And let me just show you just kind of briefly to give you a sense. You can start to see it's really getting quite messy. Although the hidden 2 extensions, there really aren't so many of them, right? There are more ADA extensions and more new extensions, hidden new and ADA extensions. Okay, but I want to go back to a situation I intentionally skipped in the 45 stem. Okay, so there's a particularly interesting thing that occurs here that I want to tell you about, and this is sort of like from the perspective of these hidden 2 extensions. This is the most interesting thing that happens in the entire range that I've studied. Okay, for 2 extensions. I just want to look just at these 5 dots. Okay, there are other elements in the 45 stem, and I'm just going to ignore them. I only want to talk about these 5 dots. Okay, when you look at these 5 dots and you look at the lines between them, your guess is that this pi 45, it looks like a Z mod 4 down at the bottom plus a Z mod 8 up above it. Okay, there's 2 dots, that's a Z mod 4, then there's 3 dot chain, that's a Z mod 8. It looks like a Z mod 4 plus a Z mod 8. Okay, I want to label these dots so that I can sort of see what's going, be a little more careful. Okay, so let's choose an element. So there's this dot here in the middle, and let's choose an element beta that it detects. Okay, but then it's also going to detect a lot of other multiples of beta. Okay, and then this next dot up, it detects 2 beta, and then it also detects 6 beta, and then finally there's this top dot that detects 4 beta. Okay, 4 beta is an element of order 2. You have 2 beta and 6 beta here. They're elements of order 4, and you have beta, 3 beta, 5 beta, 7 beta detected here. They're elements of order 8. Okay, and then down here, lower down, there's let's say we'll choose alpha, and then above that there's 2 alpha. But remember that alpha really is this dot is detecting. It's detecting lots of things, not just 2 elements. All these betas are actually, this dot is actually detecting alpha plus a, I guess, a possible multiple of 2 alpha and a possible multiple of beta. And then this second dot is detecting 2 alpha plus a possible multiple of beta. Okay, so here I've written down actual names for the elements of pi 45 in terms of where they're detected in this associated graded. Okay, now so here's the complicated thing that happens. Okay, through methods that are outside the scope of today's discussion, what you find is that, and what you'll see often on charts is you'll see a hidden extension like that. Okay, that dark green line. Okay, and that green line is a little bit sort of funny. What does it actually mean? What it really means is that if you take 4 times alpha, what happens is it ends up equaling 2 beta. Okay, and then, but then also note, and I want to write this down and I'll explain why I'm making a big deal out of this. Okay, so there are many elements detected by this dot. Okay, one of them is 2 alpha. In fact, actually, I want to rewrite this as 2 times 2 alpha. 2 alpha is one of the elements that's detected by this dot. And if you multiply by 2, you'll get this, you'll get up into here, you'll get 2 beta. That's the dark green hidden line. But 2 alpha minus beta, that's also a perfectly good element that's detected by this dot. These are really on equal footing. They're both they're just 2 elements detected by the same thing here. This guy is killed by 2. Okay, so there is an element here that's killed by 2, but it turns out there's also, but the question is, which one is it? And the difference between 2 alpha and 2 alpha minus beta is, well, first of all, they're both detected by the same dot, but the difference is that this one is a multiple of 2 and this one is not a multiple of 2. Okay, and that turns out to end up affecting the group structure. Okay, so what happens here in the end in pi 45 is the group is not Z4 plus Z8. The group actually turns out to be Z16 plus Z mod 2. And the generators could be, say, alpha could generate the Z mod 16, and then 2 alphas detected here, 4 alphas here, 8 alpha is here, and then finally 16 alpha is 0. And then we also need an element of order 2, and then that would be 2 alpha minus beta. 2 alpha minus beta is then an element of order 2 that's complementary to alpha. Okay, so and this is the bad news here is that this is actually a pretty complicated situation, and it looks like a huge mess, and analyzing all of this is actually quite a bit of work. But the good news is that this, again, as I said, this is the most interesting, the most complicated thing that occurs in this entire entire range. Okay, so in the exercises, in the first set of exercises, I put in some things there about filtrations and about associated gradients and about these maps and hidden values and so forth for you to think about for yourself. And then I think I'll stop for today.
Okay, first of all, let's thank Dan for the talk. You can unmute yourself or use the reactions or use both. Okay, now we'll open up for questions if there are any. So you can unmute yourself or you can type your questions in chat. Yeah, I have a question, like maybe a quick one. So in this case, 45, is there any like shape can be excluded by formal reasons? Like,
do you mean any possible? Are there any
potentially it can
groups that can be ruled out?
Yeah, like just by formal reasons.
Yeah. So if you have 5 dots, then what you have is a group of order 32.
Yes.
Okay, and that's actually maybe that's the first exercise, is to prove that if you have n dots in your filtration, then you have a group of order 2 to the n. But okay, all right, so it's a group of order 32, and the question is, what are the possible groups of order 32? Well, that could arise here. Well, that's actually also one of the exercises, but I don't mind talking about it because the point of the exercise is for you to think them through. I'm not going to grade you on getting the right answer, right? But here's something that can't happen. Okay, what can't happen is a Z mod 32. Okay, because if you start down here, okay, so each time you multiply by 2, you have to increase filtration by at least 1. Okay, so if you start here, then you get 2, 4, 8, and then you get to 16. So everything from here on up is killed by 16. Okay, right. But then this one could be non-zero. So you could have 2 alpha, you do have 2 alpha here, but then there's no line here. And so that says that when you take this element and you multiply by 2, you have to go at least up to here. Yeah. And then it's killed by 16. So because there's no line here, you can't have a group of order 32. Now, what's sort of interesting is that
if the gap is larger.
If the gap is larger, then something else could happen. Then it's possible that you could have that. Okay. And again, these are getting into, this is a great question, is because same question I asked. That's why I put it into the exercises. I think thinking these things through and sorting it out, is a great way of making sure that you really kind of wrap your head around what's going on here.
Yeah, thank you. Any more questions? Lectures be available. Yeah, like the materials used in the lecture will be available on the website.
Yeah, that's fine. Yeah, we'll post the lecture notes as we go.
Yeah, so the website is, I just send out the link for in the chat. Yeah, maybe so. Last chance for questions, if there's any. Okay, then let's thank Dan again for the great talk.
Okay, great.